Okay, hello everyone. So we had left off just before discussing example 8.9. This was just to consolidate what we had learned in the last class. So let's go through that. We have a beam which is shown in this figure 8.23a over here, and it is built in at A and D. So these are the two built-in points. You know what they mean. They mean that they are constrained. Okay, and it has an offset arm welded to the beam at the point B. So this offset L-shaped arm, and it is required, and there's a weight W which is attached at this end C, which you see over here. Now it is required to find the deflection of the beam at the point B. Okay, so you have to just find delta of B. Okay, so how do we proceed for a problem like this? I mean, we have dealt at several points. We have to virtually cut off this beam at some points to make it easy for us. Okay, so let's see. The effect of the arm on the beam is to supply a vertical force W and a couple WL by 3. So you want to replace this entire thing by a weight W at B. You want to replace it by this weight B and this couple which is WL by 3, because W is this weight, L by 3 is this arm. So that is what you can replace it, and then hence you will have this as your uh, free body diagram for this beam. Okay, so you will have this sorted out at B. Now with this replacement, the load intensity function which you would want to write in the form of singularity functions is let's say see it one at a time. Okay, so let's open the singularity functions in chapter 3, I guess. Let's see how we can do that. Okay, so please look at figure 3.17. Okay, in this particular figure there is a concentrated moment. Okay, over here you see this. Okay, that is given as x minus a. A is the application of that particular point, so that would be equal to L by 3, and this is minus 2. Okay, and then there is also a concentrated force which is over here W, that is x minus a minus 1. Okay, so this is what you would have as the using the singularity functions. So let's write it with this replacement. The load intensity function of Q for 0 to x to L is given by the moment which is WL by 3, and that is x minus L by 3 minus 2 minus W into x minus L by 3 minus 1. Okay, so this is it about the load intensity function which you have, and obviously there is an assumption, I guess it's about the weight of the beam which is negligible, so I guess it is negligible with respect to W. Okay, that's why you are not taking that part. Okay, now because of the built-in supports of the, so let's see what are the built-in supports. They are over here and over here. So at x is equal to 0, okay, you will have the deflection is equal to 0, and you will also have the slope of the deflection as 0. meaning that this beam which you see over here can bend something like this, but it must come back to this horizontal position at its end. Okay, so then again at x equal to L, you have the same thing. Deflection is 0 and dv by dx is equal to 0. Now you want to substitute this q into the load deflection equation, which is 8.6. Let's write that over here. Okay, 8.4, 8.6. So that equation is t2 tx square ei t2v by dx square to q. This is the equation 8.6. So what you have to do is you have to substitute from here into here, and then you would have to do integration. So you already know how these integrations work out. Okay, so that is what is expected after this. And for the integrations, I mean, you will each be thrown a constant of indefinite integration, and there will be 4 in total, because you will integrate it 4 times to eventually arrive at v. And you have 4 conditions, 1 2 3 4. So that way you will be able to find the deflection as a function of x, and then you will find the deflection at p is equal to, that would be deflection, and that would be at x equal to L by 3. So one of the things is, I think the deflection of a beam should always be reported as a positive value, but I mean this v of x will always throw you a negative number, okay, because it is bent like this, displacement is in this form. But the deflection as such should always be reported as a positive. It's just a practice. I mean, you are free not to follow it, and you won't be penalized for it, at least in this code. And but this is just for the deflection. I mean, you cannot go wrong with the displacement, because the displacement sign is sacrosanct. I mean, you can't change that. Okay, so that's how you would be able to solve the problems for deflection of a beam bending. And let's now move ahead to the next and the last topic of this particular chapter, which is energy methods. So let's see what it is. In section 2.6, if you recall, you had the Castigliano's theorem to find the deflections in simple elastic systems, and to bring and to obtain equations for determining statically indeterminate reactions. In this section, we would want to use the same for torsion and bending. Okay, and we have already developed energy method for torsion in chapter 6, bending using stresses in chapter 7, and now we want to use that to find the deflection of the beam, okay, using these energy methods. So the ideas remain the same. If you have a slender elastic shaft, okay, slender elastic shaft with the, so this is your slender elastic shaft, axis of x carries a tensile force, so this is a tensile force, twisting moment mt of x, and bending moment mb. Let me just, not necessarily towards the end, but let me just show it at any random point. mb of x. Okay, so I mean this arrow and this arrow are different. I hope you know that, in the sense, let me show this by a dotted line. So the twisting is happening, the arrow is different, and this bending, the arrow, the directions are different. So you should know this by this stage. So the total strain energy of this member would be equal to 0 to L. For the axial force, it would be F square to AE dx. The idea is the axial stress will be same throughout. Okay. Okay, and even if it's not, this formula would still work. Then you have the twisting, 2gix dx plus lmb square by 2ei dx. So one of the things which you should notice that ix is the polar moment of inertia, but I is the diametrical moment. Okay, this was referred to as IZZ if you recall. Okay, so the formulas for both of them are different. They are just calculated along different ways. So you should by this time know how to find these two separate areas. You have done it all the way in your APL 100 as well. Okay, now if this member is, and the rest of the things are, I mean, A is the cross section and E is the modulus of elasticity, G is the shear modulus. So rest of the things are somewhat standard. Now such a member may also be subjected to transverse shear. Okay, we could have also had a transverse shear force like V of X over here. Okay, but as indicated in section 7.8, the corresponding contribution to the total strain energy of a slender member can usually be neglected in comparison with the bending or twisting. So yes, there will be a shear force they can have, but that contribution will be negligible compared to the bending or twisting. This is something which was done in section 7.8. If you do not recall, please pause the video and go back and verify and confirm that that is true. Okay, so it is not that this what we are doing is valid only for shear forces which are absent. They may be present, but still we will still follow the same this formulation because that contribution due to them is negligible. Now, the Castigliano's theorem states that if the total elastic energy of a system is expressed in terms of the external loads Pi, the corresponding inline deflection delta I is given by the partial derivatives. So delta I is equal to dou U by dou Pi. If a deflection delta is desired at a point where there is no load, or in a direction which is not in line with a load, it is only necessary to introduce a fictitious load Q. This is something which we have already done, and then you sort of apply this delta is equal to dou U by dou Q, and eventually after what you get the expression, put Q is equal to 0. So this is how you would find the deflection, inline deflection along a force which doesn't exist. Okay, so this is how you can sort of solve this. Okay, so let's see this with an example. By the way, I mean, just a side note, it's also mentioned in your textbook that the Castigliano's theorem may also be used to obtain statically indeterminate reactions. Indeterminate reaction, I mean, this is something which we have done in our earlier chapters as well. What you do is you reduce to a statically determinate one. If enough statically indeterminate reactions xi are temporarily considered to be known external loads, and then if the elastic energy is expressed in terms of pi and xi, then you can easily find the inline deflection using this. So what you do is, I mean, every time you meet with a statically indeterminate system, convert it to a statically determinate system, move ahead. So let's see how we can do that. So what we do now is, first let's just come back over here. I think this is a better place. Let's just go back. Have we done example 8.2? No, this is example 8.9. Example 8.2. So we are looking at example 8.10. Okay, but it is okay. So it seems we should have gone to example 8.2. So this is something, let's leave it out to you. Example 8.10. Okay, do this yourself so that we can, it's simple, so that we can discuss something which is more complicated. Okay, so let's move ahead to example 8.11. Assuming 8.10 you will be able to do on your own. I'm leaving out 8.10 because it's somewhat straightforward and you can easily see it in your textbook. So let's go to example 8.11. Yes, so let me rub out these parts. To illustrate the applications of energy methods to statically and indeterminate systems in which slender members carry both longitudinal and bending loads, we reconsider example 8.8. Okay, so let's see, did we do example 8.8? Yes, so we have done example 8.8 and let's just see what 8.8 was. I mean 8.8 was our classic old problem. Okay, this one. So what we want to do in this question is we want I mean we have solved this problem several times right from the start of this course. So in this part we want to obtain the horizontal deflection of D by Castigliano's theorem. Okay, so let's see how we can do that. Okay, so we'll come back to the figure. Yes, so we have the same point and what we do is this, we add, because we want to now find the deflection. I mean the problem always remains the same. Where did this point D go to? Okay, so the horizontal part is okay. You had a P applied, so you can use the Castigliano's theorem. But for Q, I mean you want to find this delta H as well. So for that you introduce this 0, which is a fictitious force. I mean you don't say it's 0 right at the start. You call it a fictitious force Q and eventually you will relate it to 0. Okay, so let's see how you can do that. For the horizontal component of D, we need to apply fictitious force Q and find out the complementary strain energy. Okay, we could do that. And then differentiating it with respect to P and Q, okay, you would get, so if you differentiate partially with respect to P, you would get a delta V. You differentiate partially with respect to Q, you will get a delta H. Okay, reflection in terms of reaction, and you have to set Q equal to 0 because that was fictitious anyways. Now since the deflection point B is 0, okay, the deflection of this particular point is 0, differentiating the energy with respect to X and setting it equal energy with respect and setting it equal to 0, we can get an equation to solve for X. So X is something which you would have to find out. Okay, and so you see what they have done. I mean you had a root to X over here, but because you had added this Q over here, that Q gets transferred to X minus Q. Okay, and then over here as well to X minus Q. So this is one change which you have to take. Is when you are applying a fictitious force Q over here, it has to reflect everywhere in this problem. Okay, so for D it is simple. Okay, X minus Q because there is an X over here, and similarly for CD you should have X over here, X on this side. Okay, and then P, and you should have a X minus Q because there is a P minus Q plus P minus X plus Q. Okay, So then the moment would be P minus X plus Q into L. Okay, so you would have so using the equilibrium methods, it is possible to express all external forces and bending moments in the members CD and BD in terms of P, Q and X. Okay, so you will have to write all these equilibrium equations. Because we have done it several times, we don't actually now go into this. So that can be done for this CD, for BD as well. Okay, now then you want to find the internal force and moments along the section X in CD. So what you do is you take this X from over here, okay, from 0, take an X. Over here you write the shear force, you write the bending moment, okay, that bending moment is over here. Then you will have the axial force, okay. So these are the three things which you should have over there. And the internal force acting on BD can also be indicated in this form. So you take a distance x from this place, and then you would have axial force only. You are not taking the bending moment over here, and you are not taking the shear force over there. Okay, and there's a reason for that. I mean, right, for why would you not take a shear force in this at this particular place once you are making this internal cut? Okay, I think the answer should be with you right now. If not, please figure it out and only then move ahead. Okay, it's quite straightforward in this case. Okay, now the total strain energy in this case is due to when you say you want to write a total strain energy, you have to write it for the whole system, not for a individual rod. Okay, so that is due to longitudinal and bending loading in CD. Okay, so let's write that 0 to L x square. Let's take the longitudinal one first, x square by 2a CD, area of CD, E into dx, plus now you will have a bending, that would be 0 to L P minus X plus Q into L, this term, okay, divided by 2 EI dx, and then you will have a axial strain or longitudinal strain energy of this form, that would be 0 to root 2L, because that's the length of BD. That would be root 2 X minus Q whole square to a BD E. Okay, this term again. So there is no twisting over here, so that's why this term doesn't appear, and this is the energy of the whole system. So you have to find delta V is equal to dou U by dou P. Okay, and put Q is equal to 0. This is what it should give you for delta V at D, okay, at point D. And similarly delta H would be dou U by dou Q, Q equal to 0, and you should have a value. Okay, so both of these two things you will have in terms of X. So this you will get in terms of X. This is something also which you would get in terms of capital X. But the problem with capital X is that it is a statically indeterminate reaction. Okay, and how do you then solve the problem? We have just read about it. Now you want to find capital X. To determine capital X, we use the fact that the deflection at point C is 0. Okay, so you want to, okay, so I think in your textbook there was a quote, since the deflection, so the third dot which you see, that is actually the deflection at point C is 0. I'm sorry about this. In your textbook you can make this correction, since the deflection, the third bullet point, since the deflection at point C is 0. So that is what we want to use now to find capital X. So we want to say that the deflection at this particular point C is 0. Okay, so that would mean that you want to use this fact to find the deflection at point C. That is, according to this equation, we have according to Castigliano's theorem, you have del dou u by dou x. Okay, so this is the horizontal deflection at C, and that is equal to 0 at for q is equal to 0. Okay, and you can just solve this and you will get a value of x. So this is at C. In your textbook again, in this equation D, it is dou u by dou capital X. It is not small x. So that is also a correction which you should make, and you will get your value of capital X. Okay. Okay, so this is how you would be able to solve this example 8.11. Okay. I mean, if you haven't yet figured out, I mean, why would there be only axial force in BD and nothing else? Because this is a two force member. Okay, so as the name says, it can only have two forces and nothing else. That's like one short way, but you can have many other ways to think about it, but you must be clear of why you have not taken the bending part of it or the shear force as well. Okay, so that's where we end example example 8.11. And so one note about this which has been made is that the result which you get from this answer uh, all agrees well with the previous result, which was in example 8.8. Okay, so that tells you that your these are just two separate methods to solve the problem: Castigliano's method and the force equilibrium and strain deformation and force deformation stress strain method. Okay. So it is left to you to compare which of these two approaches is convenient. So many a time students always ask which method should we use. There is no perfect answer for this. In the sense, you have to do both of them at least on a couple of problems, and then you will yourself gain an experience of which method to use when. Okay, so sometimes it may be better to use one method, the other time it may be better to use the other method. Okay, so let's move to example 8.12. Let me just zoom in. Okay, you want to now again use the Castigliano's theorem to a member subjected to simultaneous bending and twisting. Remember, in the previous example twisting was missing, but we wanted to do that, so we have taken this question. So you have both bending and twisting in this situation, and you want to find the deflection of the tightly coiled spring in figure 8.25a. Okay, so you have a tightly coiled spring and you want to find this deflection delta. The wire has radius r. Okay, this wire has radius r, the diameter is 2r, and it forms n complete turns. Okay, so n complete turns of radius r. Okay, so this is the radius r, and 1 2 3 4, so you have n such turns. Okay, now the spring is identical to that considered in example 6.4. Okay, you can look at figure 6.18. let's see whether that is, I do recall that we have done this. Figure 6.18. Yes, I think we had, I mean, if we had not, please do have a look at example 6.4. Okay. Okay. Yeah, I think we had done that. If not, you can have a look at example 6.4. So the spring is similar to that. Except that the fact that in that case, the ends of the spring are not brought into the center. So in that example 6.4, you have something like this. Okay, over here the ends of the spring, as you see, are at the edges like this, not in the center. So that's the difference between 6.4 and this one. Okay, we shall see that this small difference that the ends are not brought to the center but are offset to this edge, has an important effect on the stiffness of the spring. So we'll see how it affects the stiffness of the spring. Everything else remains the same. Okay, so there are both torsional and bending moments appearing over here. You want to write the total complementary strain energy in terms of P and differentiating with respect to P. The deflection of the spring can be obtained. Let's see how that works. So what you do is, you just like in the previous case in 6.4, we take out one section of the spring. The wire carries at that section over here, this section. You have a transverse shear force P, okay, a twisting moment MT, a bending moment MB, okay, and you want to now apply the equilibrium equation perhaps to write some of these things. So if you write MT, that would be equal to PR 1 minus cos theta, okay, and MB is equal to PR sin theta. Okay, so the theta angle is shown, and MB will be P cross R into sin theta. Okay, so you can draw the respective force triangles, and similarly MT also would be equal to PR minus PR cos theta. So you have to apply the equilibrium equations to be able to do this part. Once that is done, and if you are not sure about it, please do it before you move ahead. There is no point in learning about Castigliono's theorem if you are not able to do these two things. Okay, so please do them, and if you may have to go back to chapter 6 and chapter the last one, chapter 7, for this if the need be. Once this is done, you want to find the energy for the overall spring. That would be entire length of this, so that would be 0 to 2 pi n. Okay, and then you will write for the twisting first, then you would do for 0.2 pi n, and then you write for bending. Okay, so one of the things that you are seeing, the length of the wire is taken as 0 to 2 pi n. That means that you are actually ignoring this part and this part in the length. Okay, and that seems to be reasonable, right? Because this part and this part may not be experiencing some of the forces, or are they small in size which you can ignore them? So what is the reason you are able to ignore this and still write the total energy of the system? Or is the system only defined as this much? So please do think about these things when you read this particular problem. So Ix and Izz are something which you can figure out based on twisting and bending. So I think for twisting you would have an Ix, and that should give you a dou is equal to dou u by dou p, delta is equal to dou u by dou p, and then you should have the answer over here. Okay, so this is one example where this Castigliano's theorem has been used to find the deflection of a beam, and just to look sort of help you, if you ever see a spring just like this spring forms something called a curved beam. It is a slightly advanced topic in the sense, if you have a usual beam, okay, it's a straight beam. It can be of any shape. It can be rectangular, it can be this eye shaped, it can be H shaped, okay, but it is originally straight in the sense the neutral axis is straight. So this is called a straight beam. On the other hand, you can have curved beams which are curved from the start itself. Okay, These are curved from the start itself, and the spring is a classic example where you have curved beams. And this is slightly more advanced topic than the usual straight beam, but I just wanted you to know this, that there is a difference over here. Though you can approximate, what you do is, at least in the cases which we are looking at, we do approximate a curved beam with the formulas of a straight beam, but in reality it may not always be true. So you must be aware of that every time you see a spring in solid mechanics, and when you dealt with the bending, for example, you should see that particular part. Okay, so there are curved beams from the start itself, and then there are bending stresses, then there are deflections in this after, say, a load is applied. Say a load is applied, this is fixed. Okay, what is the deflection in this particular? Okay, so you may have, I mean, these are also very common. I mean, if you want to say connect, say two parts and say this is a curved bridge. Okay, so then the vehicles will move over it, and then it should, the deflection and this should be reasonable. Okay, so that's where we end this particular topic, and that was perhaps yeah, the end of, I mean, we will not be learning about the limit analysis because that's more going into the plasticity, which we leave out at this stage of your career. Okay, we don't want to overburden uh, you. So I think this, knowing this is okay, not knowing what we are leaving out is fine at this stage. So in the next class we will be learning about the stability of equilibrium and buckling. Okay, that's the last of the last chapter in your textbook, and that somewhat brings us very close towards the end of this course. So today's lecture is slightly shorter than the other, but I do not want to begin the next lecture over here. So let's stop this over here, and we'll learn about buckling from the next class, and that would be the last chapter for this course for you. Thank you.